Okay, so thank you all for coming. Today we have two excellent talks. So the first one is by Giorgos Vasdekis. He's going to talk about skew-symmetric numerical schemes for SDs and where to find them.
Thank you very much, Cordina. Thank you for organizing this very nice program, actually. You and the other organizers. This is a very exciting opportunity, and I'm very happy to give a talk here. Okay, so I will talk about some recent work that I have done with Sam Livingstone, primarily, who was my postdoc supervisor at UCL. But this is also joint work with Nick Nusken, who is at King's College London, and Ray Zhang, who is now a PhD student at Lancaster University. This is about, the idea basically we are motivated by ideas that come from the literature of MCMC, Markov chain Monte Carlo, which I will remind to the crowd in 1 second. And we extend them to the context of sampling from stochastic differential equations. And the anomalous diffusion part, it's going to be that these stochastic differential equations are going to have non-Lipschitz drift. Let's say you can think of it as a connection to the program. Some of you might have seen the talk or part of the talk already, but hopefully you will enjoy it. Okay, so the motivation. The motivation is that, let's say, we wanted to do MCMC. Sam Livingstone in particular with Giorgos Zanella wanted to do MCMC. They wanted to target a distribution pi, and in order to do that, one can construct a Markov chain that converges to pi as the time goes to infinity. And then you can use the samples from the Markov chain to actually take samples from pi. In order to do that, the classic technique, the Metropolis-Hastings algorithm, is that you create your favorite Markov kernel Q, let's call it Q, which is called the proposal. This can be referred to as the proposal because it proposes a new point. And then, assuming that the Markov chain is currently at point x, you choose a new state according to your proposal, according to Q, and you go there with probability a of x comma y, where a of x comma y depends on the density pi that you want to sample from and the value q, in such a way so that the detailed balance equations are satisfied, basically. And if you do not accept this new state space, this proposed state, then you stay where you are. You do one of those two things. This is called Metropolis-Hastings. And then the game is to pick, you can pick any Q you want, pretty much, but some Q are going to work well and some Q are not going to work very well. And the game, to some extent, is to pick a nice Q. You can have various ways of picking the Q. The most simple one is to take a Q that tells you to go from x to y. You don't really care about x and y. You only care about the distance between x and y. This is also symmetric, and this is called random walk because, for obvious reasons, if you were just to follow the Q, you would basically random walk around the state space. This gamma here typically is a normal distribution or something like that, but it can be pretty much anything you want, as long as it is symmetric. This is typically quite slow. Why is it quite slow? Because maybe all your mass is close to 0, and you currently at 100, and you don't take into account the fact that you're at 100. You only take into account the fact that you're far away, but maybe you want to use information of the fact that you are at 100, let's say, to get closer to 0 quickly. And this doesn't allow you to do that. Another thing that you can do, and actually Alex has worked on this quite a lot, is you can use another algorithm that's called MALA. The proposal here takes into account local information of the gradient, in particular of the gradient of the log of pi. So here you take again a normal step, but also you take into account the grad of log pi to go to areas of higher density, of typically higher density. In some sense, this can be too fast. In particular, it relies heavily on this step size delta t here. There is this parameter delta t that you can pick as you want, but for some delta t's it's going to work well, and for some it's going to work quite badly. Because it's going to work quite badly for some delta t's, the idea that Sam Livingstone and Giorgos Zanella had was to try to use something else that is going to be a little bit more robust with respect to the step size. It's not going to work badly for step size is delta t. So the original motivation was to try to sample from this object here, q delta t. Well, the first thing is that this is not actually a probability measure. It's a probability measure up to a normalizing constant zeta that depends on x. But let's say that you want to take samples from this thing here. So, and typically you take this function g of t that is an increasing function of t, and it's of this form here. This is called Barker. This is called Barker function for historical reasons. And here the idea is that you take a step according to a random walk, but also you give an extra weight to points that have a larger density with respect to pi, let's say. So for values of y where pi is large, this takes larger values because this is an increasing function of t. So you weight it towards areas of higher density. But it's not exactly easy to target this thing. So what they decided to do was to do a Taylor expansion and try to correct with respect to this Taylor expansion, let's say. So instead of simulating from this object here immediately, they said, okay, let's take this quantity here, pi of y over pi of x. Let's write it as e to the log of this thing. So this, and if you do a first order, very naive, very simple first order Taylor expansion, this difference here, you can write it as the gradient of log pi at x times the difference here. Okay, and if you plug this thing here inside this quantity here, accounting for the fact that g is t over 1 plus t, you will get this ugly object here times this. And okay, you don't have to remember this, but actually if you might recognize this as the CDF of a logistic distribution, actually, this object here. So you can use this as your proposal, this q tilde, and if you use this q tilde decomposes to 2 times a CDF of a logistic distribution times a random walk, let's say, times a symmetric distribution. And here it is not that important the fact that this is a logistic, but it is important that it is the CDF of a symmetric distribution, in essence.
What? For any choice of gamma, so
for any choice of?
For any choice of gamma, you have the normalizing constant?
Yes, I believe, maybe it has to be, I think so, yes. Any choice of symmetric gamma, this is going to be the normalization constant, actually. Yes, yeah, that is true. The reason is that this is, actually, I'll get to that in a second. The reason is that this is a skew-symmetric distribution. Anything that is a symmetric times a CDF of a symmetric, it's called skew-symmetric distribution, and always the normalization constant is going to be 2. So why is this better than this? This is better than this because there is a simple way to simulate from this thing. There is a simple way, given x, to simulate a point y from this thing. Why? For this reason, because let's slightly change the notation. And let's say that instead of y, we want to simulate the jump, the y minus x. Let's write this as this. This is 2 times this ugly quantity here, which let's call fx of xi. Importantly, this is the CDF, so it's between 0 and 1, times a symmetric thing. Well, this thing here, because of the symmetry of the CDF, we can observe that fx at xi is 1 minus fx at minus xi, symmetric CDF, right? So if we use this for this, 2 times fx of xi, we can write this as fx of xi times gamma of xi, plus 1 minus fx at minus xi, gamma at minus xi. Right? I haven't done anything. I just use the fact that this is this plus this, and gamma is symmetric. So xi and minus xi, they take the same thing. And this has the following probabilistic interpretation, if you want to sample from this thing here. So if you're at x, in order to generate xi, either pick a value xi from the gamma and accept it with this probability here, or pick the value minus xi and reject it, reflect it with probability 1 minus fx at minus xi. Right? So either you generate this and you accept it, or you generate this and you accept it with this, which is equivalent to reject it with 1 minus this. Let's say. Cool. So, and this we call the Barker proposal. And just to give you, to summarize the Barker proposal, if you want to simulate from this thing here, you can simulate a jump from the symmetric distribution gamma, and then you can accept it, or you can reflect it with probability fx or minus 1 minus fx. And then you move to the new point, depending on whether you accepted it or you reflected it. Okay, this is a skew-symmetric distribution because you start from a symmetric distribution and then you skew it to areas of higher density or not. And this is the idea of this talk. We're going to take this scheme here, this proposal here, and we're going to put it in the context of simulating from stochastic differential equations instead of just doing MCMC, basically. Okay, cool. So stochastic differential equations, I will motivate things by saying things in one dimension in the beginning, and then we can generalize them to higher dimensions. This is a stochastic differential equation. Okay, it has obviously it has loads of applications, molecular simulation, phylogenetics. People want to simulate from the right Fisher diffusion quite a lot. But also it has applications to MCMC as well. For me, this is quite an interesting thing because these ideas are going to come in circle. Because what is the point? The point is that this is called, for example, the Langevin stochastic differential equation, overdamped stochastic differential equation. And this will be a running example. You have some pi here, which is the density that let's say you want to simulate from. You construct this stochastic differential equation here, and you know under very mild conditions, pi being in C1, that this thing is going to converge to pi, the law of this thing is going to converge to pi when t goes to infinity. So if you have a numerical scheme that discretizes this thing, immediately you can use it as a proposal to construct your favorite MCMC algorithm. So we take ideas from MCMC, we put them in the context of simulating from SDEs, and then we can use them to get back to MCMC proposals in some sense. So it's quite nice. It goes in circles from this perspective. Okay, so the idea is that let's say we're in one dimension, we want to discretize this thing. A quite naive algorithm would be to do Euler-Maruyama, for example. This is one alternative. So here you assume that the process hasn't moved that much between time 0 and time delta t. So you probably know that, so you approximate what's going to happen at time delta t by saying that the drift is going to stay constant for time delta t, and the diffusion is going to stay constant from 0 up to delta t. And this is what you get out of that. This can be quite, I'll give a toy example where this thing can fail. And the example where this thing can fail basically is when the drift is non-Lipschitz. Let's consider the case where this is something that has super light tails, minus x to the 4, let's say. And then we just do the calculations, and very easily you can see that the SD is going to be of this form here. And if you try to use Euler discretization with, let's take a large step size, delta t equal to 1. And this is going to be the Euler discretization. And if you start this from far away from the mode, let's say you start it from 10. After one step, you're going to go to 10 minus 10 to the 3, plus a small normal size around here. So this is going to be order minus 10 to the 3. Then if you take an extra step size, it's going to be minus 10 to the 3 plus 10 to the 9, plus a small normal jump, so around 10 to the 9. And then if you take another one, you're going to go to minus 10 to the 27, and so on. This is not good, because you should be, it explodes. The reason it explodes is that we started from away from the mode, and we got a very large step size. I mean, if you take a smaller step size, things are going to be fine. Here, this can be problematic. So, motivated by this, and of course, there are much better ways of discretizing the SDE, but most of them use some sort of, so they use the gradient in a local form. And if you use the gradient in a very local form, in such a way, you always run into the risk of having some such sorts of non-stability. So instead of that, what we do is we use the Skew-symmetric idea, and this is the entire talk basically. At time delta t, we create a proposal from let's say from a normal distribution, from a symmetric distribution, and either we go there or we reflect it, we'll go to the other direction. We go there with some probability p, or we go in the other direction with probability 1 minus p. And because here there is no drift has to appear somewhere if we want to approximate the stochastic differential equation. P is going to appear in here. The drift is going to appear inside the probability. Cool. So in particular, the probability of accepting or reflecting is going to depend on the current position and on the proposed jump size xi. And we have to make some assumptions in order to actually approximate the stochastic differential equation. The first assumption, actually in 1D, is without loss of generality. We just fix what is going to happen when the jump is 0, let's say. This will never happen, but it has to be a function over all the possible jumps. So let's say that at 0, it's going to be 1/2. It doesn't really matter. This is just to set up one fixed value. What does matter is that this P is differentiable with respect to the second component here. And if you plug 0 in here, then it will have to depend on the drift in this way somehow. This is because of a Taylor expansion that we have to do for P around 0. And it turns out, I will explain this in a second as well, the reason why this is the case. But it takes into account drift and sigma in that way. Let me give an example because there are many ways, many ways of picking the P here. One way of creating P's like that is to take your favorite CDF of a symmetric random variable, let's call it capital F, and let's say that the density is F, and then pick P to be of this form here. So the capital F of this quantity here. If you do this, you can convince yourself maybe that if you take the derivative with respect to Xi, just by doing a chain rule, things will cancel out and you will get the thing on the previous slide. If you plug in here the value 0, then this will be 0, and f at 0 is 1/2 because it's a symmetric CDF. So both assumptions are satisfied here. So it's just a chain rule. It's not. You need to write it down, but if you trust me, this is the case. To return to our running example, let's say we have the Langevin diffusion, and let's say that we use the logistic CDF for historic reasons, because this was where the idea came from. Then this is going to be the probability P. And just to do a sanity check, with the Langevin, we would like to go towards areas of higher density pi. So we would like P to be large when we tend to go to areas of larger density to accept them. And indeed, here P is large when Xi and the grad log pi align. You can, if you think about it, you can convince yourself that Xi and grad log pi have to align for P to be large in this particular case. So okay, this is good. Sanity check done, let's say. Okay, and then I'll just present the algorithm. The algorithm is that we want to simulate from this SD here in one dimension. We fix a step size. We fix a function P that satisfies the assumptions that I mentioned before. And assuming that currently we are at X, we sample a normal distribution 0, 1. We pick the proposed jump that takes into account the volatility matrix as well. Here it's a scalar, the volatility, and also the step size. And we go there with probability P, or we go in the other direction with probability 1 minus P. The classic, what I pretty much have been describing all this time. And then we go there, we go to this jump, and we approximate the path of the SD at time delta t to delta t and so on with these values that we have here. Okay, let me just give a kind of a proof of concept why these assumptions have been made about the P. The idea is that if you consider a test function f and you want to understand what the scheme is going to be doing after one step, this ideally you want to do a Taylor expansion, and the first order term should be the generator of the diffusion, because the generator of the diffusion gives you the derivative of this object. Ideally, it gives you the derivative of this object if I were to plug in here y, the SD. Okay, so here you can decompose this into two things. There are two levels of randomness. There is the jump, nu, and then there is whether you're going to go there or in the other direction. So this is a Bernoulli plus or minus 1, basically. So this is this thing. And then here you can do a Taylor expansion on f, pretty much. A first order Taylor expansion on f. This gets a little bit ugly, but let's say, actually before you do a first order Taylor expansion, if you were to analyze this thing, this will be 1 with probability P, so you will get this, or it's going to be minus 1 with probability 1 minus P, so you will get this. Okay, and then I will take this out for a second. There is an expectation, it's just that we're not showing it right now. And there are going to be two terms. There is going to be this term here, this product here, and there's going to be this product here. Let's just consider this product here, and let's do a Taylor expansion. And if you do a Taylor expansion, both of these things will be two polynomials with respect to delta t to the half, in essence. So the product of two polynomials is still going to be a polynomial. And it's going to be this thing here. This is the first Taylor expansion, and this is the second Taylor expansion. This is the Taylor expansion of this, and this is the Taylor expansion of this. And the 1/2 here is because P at x, 0 is 1/2 by assumption, basically. And let's consider what kind of terms we can get from the product of these two polynomials. How can we get a term of order delta t to the half? Well, the only way is to get this term here and the 1/2 here. Okay, but then there is a nu here, and there is an expectation over nu, and everything else is a constant, and nu has 0 expectation, so there is nothing of order delta t to the half. Then how can we get order delta t? We can get this term here, and get this term here as well. And if we do this, actually maybe it's easier to consider the other term. To get delta t, to get order delta t, we can get this term here and 1/2. And if we do this, then observe that we have a second order term for the test function f times nu square, which is going to be 1 under the expectation. So this plays the role of the Laplacian. This is the Laplacian on the generator of the SD. It will capture the Brownian motion part of the SD. And the other way is to get this term and this term. And if we get these two terms here, well, you can probably see that there is this is the linear term. This is the first order term for f, and there is the derivative of p. So this is, we have to match those things with the generator of the SD, and this is how we need to impose an assumption on the derivative of p at 0. Basically, this is the idea, let's say. And then there is the other term as well, but yeah, this is not that important. This is why we need the assumptions that we made. And then if we want to generalize on higher dimensions, then we do things by coordinate, in essence. For every coordinate, we decide whether we accept or we reflect. So we need a family of PIs, one for each coordinate, from 1 up to d. And if we currently are at point x, then we sample a new point according to a normal distribution. We create the jump of size nu I times the step size, and we take into account the volatility matrix. And we either go there with probability pi, or we go in the other direction with 1 minus pi. And we approximate the path at time delta t to delta t and so on with the respective numerical scheme. These are not exact, but they will get closer to the diffusion when the size delta t goes to 0, in essence. And here we need to make some more assumptions, actually, because we do everything by coordinate. It somehow means that we cannot capture any correlations that the volatility matrix may have because of the coordinate nature of the scheme. So in fact, one thing that we have to assume is that the matrix is diagonal, the volatility matrix is diagonal. It's a strict assumption. We cannot get anything if we don't have that. For MCMC purposes, this is typically going to be verified in practice. Otherwise, we just need to have a better scheme, basically. We need to have a better idea of how to update things in higher dimensions. And the other thing are just regularity conditions to essentially to guarantee existence of a strong solution for the stochastic differential equation. In particular, we want these one-sided Lipschitz. So the drift does not necessarily have to be Lipschitz, but it has to be one-sided Lipschitz. And also the volatility matrix has to be Lipschitz in this particular case. Makes sense? So these are quite standard, I think, in the literature. And then for all the PIs, the PI at x, 0 has to be a half, in complete analogy to what it was before. And the derivative with respect to the I coordinate of the jump of the PI has to satisfy the equivalent thing that it was in the one dimension. Basically, it's in a very analogous form. And in order to do that, you can pick your favorite. One way to do that: pick your favorite CDF, capital F. Pick its equivalent PDF, and take PI to be of the same form as before, given this CDF and the PDF. Okay. And then, and if we return to our running example, where we take the logistic function as the capital F pick the logistic function, the PI is going to have this ugly form here, and we call this the unadjusted Barker algorithm for diffusions, because it uses the logistic CDF, and it is motivated by things that started with a logistic CDF. But you can use other capital Fs here as well. It's not the only thing that you can use. Cool. And our main theoretical results are, well, first of all, which is kind of good, that as the step size decreases to 0, the skew-symmetric scheme is going to converge to the SD of interest, which is quite important. Otherwise, I'm just saying things that don't matter at all, pretty much. And the error is not that great. There are better schemes than that, but at least we're a bit more, it seems like we're a bit more robust with respect to the step size, but the error is going to be order delta t. in essence. By the way, the reason, the motivation behind all these things is that in some sense the drift only appears through a probability function, and the probability function is between 0 and 1. So not knowing the drift very well around, having a bad approximation of the drift is not going to screw you up that much, in essence. This is the idea, because how much can it screw you up, something between 0 and 1? Morally, this is, for me, this is morally the idea, let's say. The second thing that we can prove is if we want to sample from the limiting measure of the diffusion, let's say the diffusion converges to some pi as time t goes to infinity, then we would like to use our skew-symmetric scheme to approximate this pi. In fact, our skew-symmetric scheme, because it doesn't sample from the diffusion accurately, it's not going to converge to that limiting measure. It will have another invariant distribution, but which let's call it pi delta t being the step size of the numerical scheme. But we can show under some conditions that it's going to converge there exponentially fast. There is what's called geometric ergodicity. So we are wrong, but at least we're fast in some sense. So this is kind of the modern trend everywhere anyway. So this is good. And then we can quantify how bad we are, because we can kind of quantify under some assumptions the bias between the limiting law of the skew-symmetric scheme and the limiting law of the diffusion, which is what we would like to simulate from. We can show that it is of the error is of order delta t, and we're exploring possibilities of actually making this less, making it order delta t. The two, yes, please.
So if you know p, if you know pi, there's no way you can simply use a metropolis test.
Yes, you can do that. This is under the umbrella of doing unadjusted schemes.
Right.
But you can always, yes, you can do metropolis correction, and because the proposal is of this simple form 2 times capital F times a symmetric, you can just plug it in the metropolis correction, and everything is fine. Yeah. We just haven't explored it, but yes, you can do that. Absolutely. Yeah. Okay, cool. So a couple of so the results, just to be a bit more explicit. The first thing is to try to tackle weak convergence. In order to tackle weak convergence, we need to take our favorite test function f, let's say, that lives in, let's say it has 6 derivatives. This means polynomial growth. And we do a Taylor expansion, and we prove that the semigroup after time 1 of the skew-symmetric scheme, the first order Taylor term is going to be the generator. The second order Taylor term is going to be a very ugly operator, but at least we can write it down explicitly. I'm not writing it down because I don't want you guys to leave the room. And then some other things of less order. What is the point? The point is that if I do the equivalent Taylor expansion for the SDE, the first order term is going to be the derivative, which is the generator, plus the second order term, and blah, blah, blah. And these first 2 terms here, they match. So the distance between y at delta t and y1 is going to be delta t square. Morally, this is the idea. So after time delta t, my error is order delta t square. And then if I want to know what happens at time 1, I need to propagate this 1 over delta t times. And I get an error of delta t square each time. So overall, I get an error of delta t, right? Because delta t square times 1 over delta t. Morally, this is the idea. Now, formally, in order to do this, actually we struggled a little bit, because if we want, let's say, to use this result for x at time 2, this means that we need to use this result for conditionally on what happened at time 1, in some sense. We need to propagate once, and then we need to propagate another time. And if we want to do that, then we need to be able to plug in here a new function g, let's call it, where g is the semigroup of f after time 1, in order to condition on that. But then this begs the question: are we sure that the semigroup after time 1 of f is still regular enough so that we can plug this in here? And this was not fully obvious to us. There are some results in this direction, and actually there might be there is a possibility that there is an exact result in this direction somewhere, but this is not fully obvious to us for non-Lipschitz drifts, let's say, for a very general case. So we provided a result in this direction, and the result is the following. let's say we fix a finite time horizon and we fix a level of regularity that we want. And let's say that we consider this SD here, where I use the superscript X to denote the starting point of the SD. And let's assume all the assumptions that we made up to now, these one-sided Lipschitz conditions and all that stuff. Under all these conditions, let's take a test function that has L levels of regularity and it polynomially grows. The semigroup is well defined, it is finite, and for any starting point, this is finite as a function of X. And it has also L levels of regularity, it also has L derivatives. And also it grows polynomially fast. And so it grows polynomially fast in here. And also the derivatives, all the derivatives up to order L grow polynomially fast. And further to that, what's quite important as well is that these constants here do not depend on the t per se, they only depend on the finite time horizon, but not per se on the t. And it turns out that this is enough to give you the regularity so that you can plug in all the conditions, all the semigroups inside the Taylor expansion in some sense, and use that things. That makes sense, this as a result? Okay, so just very quickly to talk about the proof of this thing, because I was quite interested actually in that. You need to control moments basically of the most important thing to some extent is to control moments of the stochastic differential equation. So for the zero derivative, you need to control a moment of yt, and you can do an Ito expansion in essence, and the Ito expansion is going to give you something in terms of the drift at yt and the volatility at yt, which you can upper bound because of the one-sided Lipschitz conditions. And then this, you can apply the Gronwald inequality on that, and this will give you something to upper bound. And then because f is polynomially growing, the semigroup in here, you can bound this, because this is a polynomial, you can bound it in terms of the moment of y, which you know that it is upper bounded somehow. So this is the upper bound for the zero derivative. And then if you want to consider the first derivative, the problem was that we didn't have Lipschitzness on the drift. But you can consider a ball, you can leave the drift as it is inside this ball, and outside of that you can make it. Actually, we have some more assumptions that I think I forgot the slide, sorry for that. Outside of that you can make it Lipschitz in a way that it doesn't change that much. So if you call this drift mu r being the radius of the ball where you cut things down, you have quite a lot of regularity, and you can say things for the new SD, the SD YR, let's say, that depends on that. By the way, sorry, this is an extra assumption that we have to make, that forget about this R here for a second, that if we take xi times mu times xi, this is going to be bounded above by that. I was sure I had a slide for that, but yeah. Anyway, so you can leave mu r as well to be like that, and consider this SD here that depends on R, very ugly notation, but this SD here is very regular. It has a regular Lipschitz, so you can say quite a lot of things about this one, and then let R go to infinity in some sense. Okay, in particular, you can say that for this SD here, if you take the gradient with respect to the starting point, this thing will exist and it will satisfy an SD that will come basically by doing a chain rule in here. If you will take the gradient of this, and then the gradient of this, and then the gradient of this and the gradient of this. So you just do a chain rule on both of these coordinates. And if you do that, you can do exactly again an Ito expansion, and you can use Gronwald. You have everything that you have already, everything you want basically, and you can control the moments of the gradient of this thing, which also satisfies an SD. And you can do this uniformly in what R was, on what the cutoff was on the ball. That is actually the most important thing, because then you want to let R go to infinity, and you want to let out and you want to have some sort of a bound for this. And then if you have this, you can consider the semigroup that depends on the ball that you cut everything down, and using the exact same reasoning as before, because f grows polynomially, you get that in fact this thing just grows polynomially, so it is well defined, and you can make an argument and show that this thing is differentiable, because everything is smooth and nice when your drift is smooth and nice. And you can show that this is differentiable, and actually the gradient of this over x can go inside the expectation, in essence. The gradient can go inside the expectation, and inside the expectation it's just a chain rule to get this thing here. Okay? Then you can, and because everything is uniform over R, in some sense you can let R go to infinity, and you can show that the semi-groups with respect to R are going to converge to what you want. And actually, you can also get from that what you want is different. You can also get some sort of a uniform convergence in that over X. And because of that, you can get that what you want is differentiable, and the derivative is going to be the derivative of this thing here without having an R in here. So the derivative goes inside the expectation, in essence. And then you can use the polynomial bounds on F and whatever bounds you have on the moments to get polynomial bounds for the derivative as well. A bit fast, I mean a bit heuristic, but okay. Cool. Not heuristic, a little bit hand wavy, but okay. And then you can use you can inductively go to the second derivative and the third derivative and so on. Basically, once you have stuff for the second derivative, you can go to the third derivative and by using already information that you have for the second derivative. And out of all these bumbling, you get a weak convergence. In the end, this is what we get. If we want to know where the process is at time k delta t, and we want to approximate it with our numerical scheme at time k through a test function f, we know that this is going to be in expectation. We know that this is going to be order delta t, far away from each other. So this goes down as order delta t, in essence. This is called order 1 weak convergence. Now, there is work in progress for stronger form of convergence, not just weak. But the only thing, so far, what we have is for this very, very toy thing. This is very difficult to simulate from, just the constant terms. But okay, at least for this scheme here, we can get some sort of a stronger convergence. We can get pathwise convergence, in essence. If we take the expectation, if we take the norm of the difference between x at k and y at k delta t, we know that this goes down as order 1. And we believe we can extend this to more cases. This is work in progress. Why do we want this? We want this because this can give us a guarantee that if we start coupling, if we start to couple numerical schemes, either with a process or with themselves, a numerical scheme with step size delta t and a numerical scheme with step size delta t over 2, that this coupling is going to work quite nicely and that we can compare them with each other. And this might allow us to create multi-level Monte Carlo what's called multi-level Monte Carlo from this technique, which is to create copies with different step size and compare them between them to reduce the variance, in essence. Okay, cool. Another thing is that, as I said, we fix the step size delta t and we try to understand what's going to happen when the time goes to infinity, when the skew-symmetric scheme's time goes to infinity. For this, we need to make some more assumptions. Remember, the matrix is diagonal, so only sigma i's matter. But we also need to have upper and lower bound for the sigma i's for this particular case. I think it works more generally, but for now, this is the assumption. This is a bit more important. We need essentially light tails. We need the drift to tell you that if you're very far to the right, the drift is going to tell you come to the center, in essence. And if you're very far to the left, the drift will tell you come back to the center as well. This is what this thing tells you. If you're very far to the left, you want to go back to the right. And if you're very far to the right, you will want to go back to the left. And the other thing is that this needs to be accounted for. I mean, this is an element of the diffusion. We can't do anything about that. This is an element of our scheme. It tells you through the probability of accepting or reflecting, it tells you that if you, let's say you're very far to the right and you propose to go even further to the right, this will go to 0. This won't happen. Whereas if you propose to go to the left, this will happen almost surely in some sense. This is what this thing tells you. Quite reasonable. Typically you can check that in practice through this construction with the capital Fs that we have constructed. Okay, and if you have that, then you can guarantee that the skew-symmetric scheme has an invariant measure pi delta t with all moments finite, which also means that it is important in some sense for the thing that you want to start, the pi that you want to target also needs to have quite light tails as well for this to be a reasonable approximation. But also we get geometric ergodicity, what's called geometric ergodicity. So in total variation distance, the distance of the law at time n and the pi delta t goes down exponentially fast. there are quite classic Lyapunov arguments. You construct what's called the Lyapunov function, and it's quite easy to get that to get this result. It's quite standard. This also immediately gives you a central limit theorem for your skew-symmetric scheme, which is in the context of MCMC. This is quite important as a theoretical guarantee that you won't get blown. Your estimator is not gonna blow up, let's say. Okay, and some more assumptions to get the final thing about the bias. This is one extra assumption that okay, maybe the drift does not have to be Lipschitz, but it kind of has to show to tell you that you have to go in the right direction. So the dot product between mu and x has to be negative, and it has to be this kind of negative, let's say. This if you think about it in the one dimension, this means mu times x less than that. So mu has to be less than minus x to the minus 1 plus a. So this does not allow for anything that has super heavy tails, like a Cauchy distribution or stuff like that. This won't be satisfied here for the Langevin stochastic differential equation. But as long as you have something that is at least exponential, that has at most exponential tails, this is quite easy to. I think this is typically going to be verified. Then, of course, we want the diffusion to have an invariant measure and to converge there. Otherwise, there is no point in what I'm going to say. We need the limiting measure to have all the moments finite, and we need some sort of a regularity. So the log of pi has to be C4, has to grow polynomially. Itself, the pi has to be C4, of course. Anything of the form e to the minus a polynomial is going to satisfy those things. This is not that bad in essence. Cool. And then as long as we have this, then we can guarantee that the bias, take your favorite test function f, integrate it with respect to the limiting measure of the skew-symmetric scheme, compare it with the integral according to what you would like to get. The error is going to be of order delta t, basically. And we have some ideas on trying to make these are actually order delta t to the 2, but we're not there yet. Yes?
So in the previous slide, you had this result with the geometric recordistic. Presumably, somewhere there in the assumptions, you also need the original process to be geometrically recorded.
There is a chance that this is implied by these things here, by the fact that the drift is. Yeah. So I can't fully answer this. I think this is correct. I think this might be implied by the fact that the drift goes down. At least in the Langevin, this is typically the case, right? That if the gradient vanishes, then you don't have geometric recordisticity, and if not, typically you have. If it goes to infinity, you typically get geometric recordisticity, I think. Yeah, I would assume that I think somehow it is hidden. Yeah, I would assume that it's somehow hidden there. Yeah. Okay, cool. And a few simulations. I mean, they're kind of toy. There are toy examples. This is the first thing. This is an Ornstein-Uhlenberg process, and we know the good thing about this is that we know exactly what the law is going to be at time, let's say 5. So we consider the law at time 5, I think, in this particular case, and we try to generate samples using 3 different schemes. This is a naive Euler discretization, which works perfectly in that setting, actually. The Euler is constructed to be perfect in this setting, in essence. And then this is the black one. Our scheme is the red one. And we also compare against what is called the tamed Euler, which is another way of creating schemes that are robust with respect to the step size, that they don't fully take into account the gradient. They only take into account a normalized version of the gradient that doesn't allow you to escape a region of, let's say, -1, 1 somehow. They create a threshold in some sense. You can't go further out of there. And this is the step size. We used various step sizes, and this is the error that we had. And okay, we are sandwiched by the other 2 techniques. Of course, the Euler works amazingly here, but at least we do in this particular case, we do a little bit better than the tamed Euler. Okay, another example is an example that it's quite well known in Bayesian statistics, which most of our motivation comes from. This is a hierarchical model in Bayesian statistics. It's called Poisson random effect. Your data points, given some parameters eta I, follow a Poisson with e to the eta I. And then the hierarchy comes from the fact that eta I also follows a distribution given a mu. And this mu has a prior distribution normal. In this particular case, we set mu equal to 5. We generated the data points according to this. These data points induce now a posterior distribution on the parameter space, which is a 51-dimensional parameter space. This posterior distribution creates an overdamped Langevin according to this. And we use our skew-symmetric scheme to target this Langevin diffusion. Okay, and we compare against just a simple Euler, actually against a tamed Euler as well, but the tamed Euler is not here. So here we compare ergodic averages of the skew-symmetric schemes in order to target from to take samples to approximate the posterior in the end. We use various step sizes. Ours is the red one. The Euler scheme is the black one. You see that the Euler really fails after some point when the step size becomes large. It's the same thing as what I showed on the very first slide, that when delta t is 1, there are problems of stability. And you see that our scheme is quite a lot more robust with respect to that, so at least that's nice. Here we initialize the scheme in a different location, I think, but similar behavior. And what I should also say that we have some simulations where we also compare against the tamed Euler, and both the red and the tamed Euler seem pretty similar in that sense. We do a little bit better in this particular case, but in essence they are quite similar. So at least, you know, we can suggest an alternative method to tamed Euler and using skew-symmetric distributions, and it seems like the performance is in many ways quite similar. And the last one, the last example comes from the physics. Let's say we live in R2 and we have 50 spheres which move according to a stochastic differential equation, but kind of interact with each other a little bit as well. So the drift for the diffusion part is just very simple, a constant here. The drift is something super linear that tells the balls that they have to come back to the center. And also there is a bit of some sort of some interaction, let's say, in the drift between the balls. And we use two algorithms here to simulate this thing, our algorithm and a simple Euler. And the game was pretty simple. Well, okay, so before I say that, let's say, observe that this parameter here, B, the larger it is, the more the non-Lipschitzness, the larger the non-Lipschitzness in some sense, the larger in some sense. And there is a step size that we also will use in the algorithm. And we just try to understand how many times is the algorithm going to explode. Is going to work really, really badly, basically. And our algorithm doesn't work badly because, okay, I'll get to that. So we create pairs of parameter beta that tells you how bad your Lipschitz is, and also step size delta t. So for any pair of delta t and beta, we run a lot of simulations from Euler, Maruyama, and skew-symmetric, and we counted how many times did the scheme explode. Here you see that the scheme exploded every possible time, whereas here it didn't, and there is some area here which creates a nice probably SLE curve or something like that, where things are somewhere in the middle, let's say, whereas our scheme never exploded. And of course, our scheme, it's quite easy to understand that our scheme didn't explode because we just sampled from a normal random variable, and we just went there or in the other direction. Whereas here you can see how easy it is to screw things up in some sense. Cool. That's it. These are, okay, very nice. These are some references. This is our paper. It has this very long title, Skew-symmetric schemes for stochastic differential equations with non-Lipschitz drift and unadjusted Barker algorithm. I didn't pick the title. Here, if you want to know more about the Barker proposal, which motivated these things, this is the main paper by Sam Livingstone and Giorgos Zanella. But also a very nice paper to read is with these two and also Max Hurd, who is a PhD student at UCL right now. This is a review paper. It's quite nice. Motivates things in a very nice way, I think. And this is, that's it. Thank you very much. Thanks.
So from the results, you showed the one result where in the linear case, the OU process, you seem to be doing a bit better than the trained state Euler. That sounds reasonable. Why this should happen?
No, I don't know. I'm not sure.
Beyond the one, right? Sides.
Well, they can also go between. So just to explain what they do. Okay, maybe this is a good way to use the chalk. Thank you very much. So I mean, the answer is I'm not entirely sure, and I don't think that this is enough to extrapolate that we do better or something like that generally, right? I mean, it's I think it's just an example. Yes. So I think, and I might be writing something idiotic, but I think pretty much what they do is, let's say they have a step size here, grad log u. Plus noise. I don't know. Something like this. So in essence, it's something like this. So in essence, they don't allow this to be larger than 1 or -1. They create this kind of a cutoff. But yes, and okay, from that perspective, we could be. But yes, so you're right. I guess you're right. But typically, when you take a sample from normal 0, 1, you're still probably not going to be that much far out. Yeah, but this is probably the reason, to be honest, that we allow values that are not necessarily strictly between -1 and 1 on the. Maybe this is the reason. I think so. Yes, I think so. I think they have probably have stronger form of convergence, but I think it's still order 1. Don't quote me on this, but I think this is the case. Yes.
So, right at the start, you've got the assumptions on P. So it's like P of x0 equals half, and then on the derivative as well, you've got this in terms of sky, you've got.
Yes.
You've got these assumptions, and you're saying if you then pick f to be the CDF of a two-dimensional variable, that's the assumption.
Yeah.
Can you go? But that doesn't hold the other way.
No.
So
No.
Which isn't using this f, which might be good, or is this just?
Well, yeah. For example, okay. So you take your favorite f. Let's call it f1. Take your second favorite f. Call it f2, and take any convex combination of those two. It's still gonna work. So there are many more things. And if you think about it, this is quite as a let's say a space. This is a lot large. This is super large because fix your x, and view this as just as a function of xi. This just tells you that this is this is just a differentiable function of xi, which is between 0 and 1 because it's a probability. And at 0 it is equal to a half, and that and the first derivative at 0 has a particular constant. This is it. You can take whatever you want. You can just make it be like that, and then outside of that, make it whatever you want. Basically, you can smooth it out in any way that you want. So it's a huge space. It's just that for practical reasons, we use this construction here, but it's not.
But there's no like obvious choice from. This construction.
Yeah. Okay. So it's a very nice question. It's a very nice question. Let me get to that very quickly. Okay. So before I get to that, let me remind you this thing here on the Taylor expansion. The first derivative is the generator, and the second derivative is this operator A, which we have an explicit formula for that. If you can, and this operator A is going to depend on the second derivative of P at 0. If you can make this such that for any test function, you integrate this with respect to p and you make it equal to 0. If you can solve this equation, then you can make the scheme order delta t to the half in the limit. The bias between the limiting measure of this scheme and the diffusions is going to be delta t to the half in that particular case. So this can give you an equation and a methodological way to pick p, but we don't have a clear expression for p for that yet. Yeah.
One question. In your ergodicity result,
Yeah.
How important is that you have ergodicity with respect to total variation distance? Because it's
This is
actually
the classic thing that has been happening in the literature for many years. I think now it's as people have started thinking about Wasserstein distances and stuff like that.
What I can say, in this way you show your coefficient. Right?
Okay, yeah.
So in particular, in this reason, because this reason you need the diffusion coefficient is ready.
Yeah,
It does not vanish.
yeah,
In order to get your disability and ergodicity.
indeed, yeah, yeah.
You can also consider the same thing with respect to Wasserstein distance,
Okay, yeah,
which allows singularity of the diffusion coefficient. You can also
it's good, yeah.
convergence geometric ergodicity with respect to Wasserstein distance. So I don't know whether this affects your later results.
Yeah, I don't know. I'm not sure how. So the way we prove it with the total variation is that we just consider a Lyapunov function. We find a nice Lyapunov function that does the job. And I'm not sure how easy it would be to get a coupling to get the Wasserstein
There are
result
lots of
somehow.
ways.
But yeah, okay. I mean, then it would be a very nice thing to do.
Because all your examples have the head.
Yeah, yeah, yeah.
This would allow you also to look at it.
No problem.
I lost somehow at some point the regularity that you asked on the drift and the diffusion.
Okay, yeah.
How far can you go with shifts? You want it in shifts, but how irregular?
Okay, so here we assume C infinity, but you don't really need you don't need C infinity. You need as many. Okay, so you need here for this result, your test function has to have 6 derivatives. Pretty much the drift has to have as many derivatives as this one here.
Because indeed I was interpreting how, when you are in one dimension at least, what you are doing seems like, which is not what you do,
Yeah, yeah.
but you transfer, so to take a martingale example, so you use the scale function to reduce your martingale. That's
Okay,
that's
yeah.
what happens, that's why you have the mu over the sigma square.
Okay, yeah.
What you do is to transfer it to a test function and remove the second order term in this way, so impose something on the test function in such a way that you remove the drift.
Yeah, that's a nice way to think about it, yeah.
Therefore, I thought that in that case you could relax a little bit the assumption and take some piecewise regularity, for instance.
Okay. Okay.
And but I don't know. And then it seems maybe, but maybe we can discuss later.
Yeah, 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 of course.
That it seems to me that the regularity may come up in the proof of the regularity of the.
This is where it comes up. This is where it comes up. And also, I think pretty much this is where it comes up. I don't think that it is needed anywhere else. Because outside of that, when you do the Taylor expansion for the skew-symmetric scheme, the mu doesn't really appear anywhere in essence. It's, yeah. Yeah, 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 exactly. Yeah. Sorry, we overtook our welcome, but yeah. I mean, we can discuss this, yeah.
Thank you all very much. Thank you. Thank you, the speaker.